All right, ladies and gentlemen, why don't we go ahead and start again? What I want to talk about now is something I probably should have brought up before, but doing lectures like this is almost like a performance art where you don't have a whole lot of choice about if you make a mistake, you can't go back and fix everything. So we're just going to go with this as best we can and see how things turn out. Sound good to you? I think it sounds great to me. All right, I want to talk generally about nucleophilic acyl substitutions, which is really what we've been talking about for the past 2 or 3 episodes. Now, acyl is a really old-fashioned chemistry word for a carbonyl. If we want to, and this isn't perfect, but it works as a general statement, if we want to kind of summarize what all nucleophilic acyl substitutions look like, it would be this. Where you replace the X on the acyl group with the nucleophile and you produce X with a pair of electrons. Could it be an anion? Sure. Could it be neutral? Absolutely. Either way, though, it's going to pick up a spare pair of electrons. So what we need to think about is this. What can we say about this X group? Well, we can go all the way back to your friend and mine, the pKa table, where pKa, remember, was a really good measure of the stability of a leaving group. The pKa was a good measure of the stability of a leaving group. So can we apply that here? Yes, let's. All right? So we're going to start with a pretty simple one, your friend and mine, the acid chloride. We react this with a nucleophile, and we're going to get this plus Cl anion. All right, I'm going to draw a separate line over here for reasons that will become apparent soon. All right, for the anhydride, yuck, that was terrible. For the anhydride, what we get is this. For an ester, we're not even going to talk about the acid because we've had several discussions about OH being a crappy leaving group. But for an ester with the nucleophilic attack, what we get is we're assuming that structure is going to be the same through all of them, plus that, the alkoxy anion. Amide with a nucleophile gives you this, plus and we're not even going to discuss the salt because I don't want to know what the pKa of a salt would be. So let's take this list: the chloride, the carbonate, the chloride, the carboxylate, the alkoxide, and that amide ion. Let's redraw these over here. Just what we had on the last page. Now, what would these look like if we protonated them? Well, they would look like, sorry, wrong color. They would look like this. For the chloride, it would be HCl. For the anhydride leaving group, it would be that acid, this alcohol and that amine, in this case, ammonia. All right, sounds good. The pKa's for each of these. Now, as always, I do not expect you to have pKa's memorized. This is a resource I don't think you should have to take up valuable brain space with. But the pKa of HCl is around -6, of the carboxylate is 4, the alcohol is 17, and the amide here is about 35. Wow, that's some pretty big jumps there. We're at a 10 to the 41st difference in terms of acidity. So what we can say about this list is the goodness, the goodness of the leaving group increases as we go up that chart, where the chloride is the best and the amide is the worst. So chlorides make a much better leaving group than the amides do. We can use this analysis throughout all of the discussions of carbonyl chemistry. Another way we can use it is this. I know I've been going on for quite a while about how you cannot move up that derivative table. You can only move down or go back to the parent carboxylic acid. So let's take a look at this. Let's look at this ester. And let's say we want to react it with chloride. And our goal here being we generate the acid chloride plus the methoxide anion. Now, the way we can do this study, or the way we can do this analysis, is this. What is the pKa of this chlorine if it had a proton? Well, the answer to that is the pKa is equal to, what did I say on the last page? -6. The pKa is equal to -6, whereas the pKa of this alkoxide, if it were an alcohol, is 17. Now you can tell from looking at these that the chloride is better off on its own, it's more stable on its own than, say, this alkoxide is. So one thing you can say about this, if you wanted to get really upfront about it, is this reaction will not happen. But unfortunately, like most things in chemistry, you need to avoid saying always and never as much as you can. There could be an equilibrium here, but the equilibrium would look something like this. It would, I drew that backwards. That's really funny. Hey, I'm just seeing if any of you were paying attention, and you were. Thanks for that. The equilibrium would look like this. Where almost all this material favors this side. And you can use that analysis over and over and over again. Now, let's flip back a page. Two of these really suck, I'll be honest with you. Those two leaving groups are really terrible. So what does that mean? Well, if you're dealing with a structure like, say, this, and you want to do something... Sorry, folks, I'm not sure when that cut off, so I'm just kind of go back and repeat some of this. So let's say we've got these two situations. We can have the ester, which turns into an amide, or we can have the amide, which turns into the acid. Can you do these? Absolutely, yes, you can. What you cannot... When it comes to reactivity, the ester is pretty much equal to the carboxylic acid. So, there you have it. There's what this stuff means for you in terms of leaving group. So, I'm going to leaving group from this discussion right now. My side. Anyway, I'm going to leave now, and then tomorrow, or the next time I decide to film, we will carry on discussing the reactions of acids and esters, and finally amides. Have a great day, everybody.